Okay, here I think I got one question from the chat. What power are we talking about here? So here we are talking about the dynamic power. So here we are talking about the dynamic power. Okay, so let's know is the power per transistor. I will go to that point. So we will talk about the power per transistor and power of the total chip. So this is the original paper by the Dennard. Okay, so I will not go through the original paper, but we are going to derive some of those conclusions from the Dennard scaling using the same approach as in this original paper. Okay, so let's do it. So here, let's do the scaling, assuming those assumptions. So let's do the scaling factor x. So in the nth generation, so here we have those key dimensions of the transistor, like the TOX, which is the thickness of the oxide. W, is the W width of the transistor. L is the gate length from the source to the drain. So basically 3 dimensions of the structure in the transistor. Those are key dimensions. And we are going to assume those key dimensions scale by this factor x from generation to generation. So all of those becomes divided by x. Meanwhile, we will assume the voltage VDD will also decrease by x. And also we have to assume another voltage, which is threshold voltage, also decrease by x. So let's say all the voltage decrease by x. Meanwhile, if we want to maintain this circuit perform well, we have to assume the density of the doping increase by x. So this may not be a good assumption. We will see it later, but let's assume it for now. So the density will increase by x for the doping. Okay, so this is the assumption. And then we're going to talk about that in more details. Question, why did Dennard say that electric field in scaling remains the same? Okay, so that's a good question. So let's, I plan to talk about this later, but we can discuss first right now, since you asked this question. So this is the constant field scaling. Why is that? Because if you look at the electric field vertically across the oxide, it remains the same. Because here, when we run the transistor in the on state, you're going to apply VDD to the gate, and then the electric field in the gate oxide will be this VDD divided by TOX. So if VDD scales by x and also your TOX scales by x, then this is a constant field. Similarly, this is from the source to the drain. You apply VDD to the drain for the on state. So then you have the horizontal field from the drain to source. And this field is VDD divided by L. And again, VDD scales by x, L scales by x. So this is constant. So that's why this is a constant field scaling. Does this make sense? All right. So this is our assumption, and let's do the derivation for the next. So let's assume the total chip area is A, and the area of a single transistor in nth generation is W times L. Of course, the area will be larger than W times L because you still have the source and the drain. But let's use the W times L, which is the gate area. as the measure of the area for the transistor, because the source and drain will be proportional to this area. So let's use this to stand for the area for one single transistor. If we assume the area of a transistor is given by W times L, then the number of transistors in nth generation will be the total chip area divided by a single transistor area, WL. So then you get this NN. This is number of the transistor on this chip. Then let's assume the scaling to the next generation, N plus 1. So the dimensions of the W and L will decrease by X. So W times L will decrease by X squared. Okay. That means the number of transistors will increase by X squared, because let's assume the total chip area is the same. Just assume this is the same, this is constant. Then the W times L now reduced by X squared. Then the total number of the transistor will become X squared times the original number. So this means the density of the transistor increase. So this is the next Moore's law. Okay. And next, we are going to derive the delay. So this is the dynamic scaling. So if you want to get the delay, okay, and we have talked about the delay for inverter. So let's use that as example. So actually, for all the digital circuit, the delay is and let's say generic is the capacitance of the node times the power supply divided by the on-state current of the transistor. So this capacitance, okay, is like, let's say one inverter is driving another inverter. So the second inverter's gate capacitance is like the node to the first inverter. So we're interested in this gate capacitance. Okay. So what is the gate capacitance? This will be a load for the first inverter. So the capacitance at the nth generation is this COX. So this term is the COX. The gate oxide capacitance per unit area is the epsilon 0 permittivity of vacuum times the epsilon of oxide. And this permittivity of this oxide material divided by the thickness of the oxide. So this is COX. But this per unit area, you need to multiply by the gate area, which is W times L, which is this. This W times this L will give you a total area for the gate. So then if you multiply by that, then you get the gate capacitance for the node as a node capacitance. And let's do the scaling now. So here all the dimensions scale by a factor of x. So W becomes W divided by x, L becomes L divided by x, TOX becomes TOX divided by x. And those two are the physical constants. So here you can cancel those two, and still you have 1x left in the denominator. That means the capacitance will decrease by x with the scaling. So this is capacitance, and then let's look at the on-state current. And the on-state current is determined by the saturation current when the gate voltage becomes VDD. So then this is the saturation current equation, mu COX W over L, and then VDD minus VT squared. So let's do the scaling. And first, the COX will increase by become COX times X. This is because here you see the COX here is determined by the 1 over TOX, and TOX become scaled. Then the oxide capacitance will increase because the TOX is the denominator. So oxide capacitance will increase. So then COX will become COX times X. And then similarly, W will become W over X, and L will become L over X. And we'll assume all the voltages scale. So the voltage VDD will become VDD divided by X, and threshold voltage will become threshold voltage divided by X. So you can have all those, and then you can cancel some of them. And here you have a squared. So then you times X, but you have squared in the denominator. So you still eventually get X in the denominator. So here the conclusion is the current decrease by X. So, this is a good question. Why is the threshold voltage scaled by X when the doping density is multiplied by X? So the answer to your question is this is a wrong assumption. Okay. So the threshold voltage actually will increase with increased doping. But here, let's assume this for now. I will talk about that later. So that's why I will say the standard scaling is not realistic in practice. So I will go to that point later. So this is the assumption. The threshold voltage is scaled by X. This is to make these equations simpler. Otherwise, if you don't have this one, then it's hard to get this kind of conclusion. So, but that is a wrong assumption. Okay. So let's do that. So then eventually the delay, you plug in the C becomes C divided by X, I become I divided by X, VDD become VDD divided by X. So eventually you still have X in the denominator. So that means the delay will decrease by X. Okay. So the circuit becomes faster because delay decrease. Or in other words, your maximum frequency you can run the circuit, is 1 over 2t, 2tp delay. So the f will increase by x, the maximum frequency you can run the circuit. So this is the conclusion if we follow this kind of standard scaling rule. Any questions here? Next, let's see the power. Okay, the power is given by this formula. Let's say the dynamic power. You have seen this C times VDD squared times F. So let's do it. CL will become CL divided by X, VDD divided by X, and F, as we showed in the previous slide, will increase by X. So if we do that, then here the power per logic gate, for example, the inverter, will decrease by X squared. So this is the power per circuit module, like this inverter. The power will decrease by X squared. But you have more transistors on the chip, you have more modules on the chip. So you have like X squared more circuit on the chip. So the total power on the chip will be the same, because if you use this one multiply by this one, use the power per circuit multiply how many circuits you have on the chip, then you get the total power. So the total power on the chip will be the same. And here we assume the chip area is the same. We assume the chip area is a constant. So that means the power density which is measured by, let's say, in the units of watts. Watt divided by centimeter square. So let's say this power density does not change for the total chip. So that's the conclusion from the standard scaling. Any questions? So per circuit, the power reduced, but you have more circuits on the chip. so the total power remains the same, but each circuit becomes faster. So that's the Daniel scaling conclusions. We can summarize that into this table. So here, this is assumption, and all the dimensions TOX, LW, and XJ, we didn't talk about that. That is the junction depth. So we will ignore that for now because the most important thing is the first three dimensions. And then doping concentration increase and the voltage decrease. So those are the assumptions, and they can derive some of the device transistor level parameters, like those field and the capacitance and the drift current and so on. I will skip that. We can directly jump to the circuit performance as we derived. So the circuit delay per circuit, like your inverter, will reduce by 1 over x. This is what we derived. And also the power dissipation per circuit, like one inverter, then will become 1 over x squared. So the circuit density is the, let's say, number of transistors or number of circuits on the chip, number of transistor becomes x squared. So then if you use the power dissipation per circuit and the number of transistor or number of circuits, you use those two multiply together, then you get the total power density, because this is P, this is 1 over A. So you get the total power density, P over A, and this will become 1. This is power density. So this is the conclusion we have from the Daniel scaling if we use this constant field scaling. Let me